Okay, so what I thought I'd do is maybe just explain a little bit the title, Big and Fast Data. So I'm sure everyone here has heard a lot about big data before, but maybe not as much about fast data. What I mean when I refer to fast data is we deal a lot with data that is continuously coming at you, right? So far, most of the analysis tools that you were looking at, they were tools that would help you with retrospective analysis, where you go back and try to look at something that might have happened and try to figure out, what went wrong or that sort of thing. In the city especially, but there are a lot of other use cases as well. There's an environment where there is a lot of data that is continuously being generated, and if people are able to harness that, get insights from it, then they can make better decisions about how to optimize the system, fix faults, assign resources, priorities, and that sort of thing. And that's a really big challenge within the city, as I said. So what I thought I'd try to do is try to explain to you examples of projects that we're doing that are both, in some cases it's big data, but it's big data because it accumulated over a long period of time. In some cases, it's big data every instant. Right, you're continuously getting, hundreds, thousands of data points potentially, per second. So I'll talk some about that. Now, before I get into, the research that we actually do, I thought it might be worthwhile to introduce IBM Research, because I'm not sure how many people here have actually worked with IBM Research before. Truthfully, if you've met someone from IBM, you've probably met someone from our sales department, or or possibly from the product division. And research tends to stay behind the scenes, so less people are familiar with the research organization. Of course, most of you are researchers, so that it may be different here. So there's probably two big things if you want to try to think about how to define research and what do we think is characteristic of of IBM Research and how we go about solving problems and doing research. So I have exactly two charts to try to explain to you IBM Research. So the first chart is, and this is the first property, is that what we try to do is we try to do things that are are far out, but we also try to make sure that maybe some of them can somehow make it out into the real world, because sometimes if you go too far out, it doesn't quite make it into the real world. And so there are two interesting things about this chart. So one of them is that if you look at the items on this chart, right? So Mark I was like you can think of it as the first mainframe. It was the first sequential calculator. Fortran, one of the first high-level programming languages. DB2 or relational databases was the beginning, or DB2 is the beginning of relational databases. The scanning tunneling microscope you may be familiar with. That's kind of people see that as the beginning of nanotechnology, because you're able to finally start operating at that scale. The first chess-playing computer. So what's interesting about this is it's two things. One is that these are things that people associate with IBM, and yet they all came from research, right? So IBM is a 450,000 member organization. Research is less than 1% of that. We're about 3,000, which is actually still quite large for a research organization, but nonetheless, it's a very small percentage of the company to have this many of those things that are kind of iconic for IBM to all come from research. That's one piece. The second part is that it's how we think of research. We say, what is the mission of IBM Research to the company and to the world? And we actually think of our mission that way, that it's not just to the company, and it's to try to advance science and technology, but probably even more importantly, it's to try to look out and either create or identify that which is disruptive, and then figure out how to harness it, right? And all of these things were kind of along that lines, where something disruptive was happening, and we were figuring out how to make it, exploitable, so to speak. So that's one aspect, is that we do try to reach further out. We try to look at these inflection points, but we also try to make sure that it can, at least some things can make it out through our products. Not everything can. If everything made it out through our product group, then we would be the product group. We wouldn't be the research group. But at least to have some things is important. The second thing is that in terms of our researchers and the environment that we try to provide for them, we try to provide an environment for researchers such that they could pursue the same types of top accolades that a professor at a university would go after. So we have people who have been Nobel laureates, Turing Award winners, National Academy of Science, National Academy of Engineering. So obviously we go after a definition of research that's not just about the next gen of our products, but it's really about trying to do world-class research that is recognized as such. So I would say that those are probably the two things to maybe think about as you think about IBM research. So this chart it shows that I talked about that there are 3,000 members in the IBM research organization worldwide, and they're located in 11 labs. So what's interesting about this chart was that there were 8 research labs up until 2010. And in 2010, no new research labs for roughly over a decade, actually. And the last new labs were when we moved into India and China and those sorts of things, about the same time that many other people were moving into it. And we tend to locate our labs where we're trying to take advantage of the talent, so where there are rich talent pools, and we try to move in and have a research lab and be able to leverage that. Two things that were kind of different about the 3 labs that were established in 2010. So I guess the first thing was it's quite a bold statement in the middle of a recession. 2010, we opened 3 new labs, all of them roughly to grow to around 200 members. So that's very significant. The second thing is that all 3 of these labs, they went to, what we realized by putting labs in different locations was not only could we take advantage of the talent that was there, but we realized that it gave us much better information about the challenges and the problems and how people would want to try to use technology. And that helped us to better shape a research strategy. And so the 3 new labs were actually not just about leveraging talent in the area, but it was also leveraging the challenges and the problems in that area and finding a space where that would be good to do. So we wanted to get more muscle behind what we refer to as Smarter Planet and Smarter Cities. Now, you may well have seen the advertisements for Smarter Planet and Smarter Cities, and it's kind of nice because it means you can explain to your mom, or to your grandparents that, I'm working on things that will make the world a better place, and so that's quite nice. And throughout the rest of the presentation, I'll talk about what that really means and how it translates into things that we do. But all 3 of the labs were focused on those. So Brazil, natural resources, as you might imagine, chemical and petroleum is a very important topic in Brazil. Agriculture is a very important topic in Brazil, and so the lab there is focused on those things. In Australia, mining is important, and water scarcity is important, and so there again, natural resources was the focus. And the Dublin lab was selected to go after smarter cities. So it's currently the only smarter cities lab, smarter cities research lab for IBM. And we actually chose, a lot of people ask me, why did you decide to put the Smarter Cities lab in Dublin, right? So if you think about it, IBM's a commercial company, where's the biggest money? The biggest money must be in the biggest cities. So Dublin is obviously not the biggest city in the world, so why would you put it there? Well, several reasons. One is that, truthfully, we have labs in some of the other locations where there are the mega cities that are popping up. The other thing is that we felt like, in terms of smarter cities, it's not just about getting the most people into the smallest space and then trying to optimize in that way. It's about creating cities that are healthy and that people can have a quality of life that's representative. It's about communities and these sorts of things. And so we felt like European cities actually had a lot to give in that space, and so that was one aspect of it. The other aspect was that Dublin actually stepped forward and said, you know what, if you locate the lab here, we'll give you access to all of our data in the city. So the GPS probes in the buses and the induction loops in the road and the closed circuit TV cameras and the meters that are on that tell us the energy consumption, telemetry that we use for our water resources. You can have it, and you can have access to our subject matter experts, so the people that run the transportation department, the people that run the water department, and so on. You can talk with them. In fact, they went so far as to say, we're offering up Dublin as a test bed for IBM research. And we kind of cringed when they said that that's what they were going to do the press release on, because we thought surely there would be rioting in the streets because people wouldn't want to be guinea pigs for IBM research. But But no, they went forward with it, and actually the people are quite excited about kind of being part of that movement. So that's a little bit about the why. And I'll talk a lot more about how we go about smarter cities throughout this. So maybe the next question that you might have is, why cities? Why now? Why is that important? And with this chart, you probably have heard the statistic, right, that we've, in 2010, we passed the mark where 50% of the world's population actually live in urban regions, and that's a first time. And probably even more importantly, that the trend is significantly upward in terms of the expectation. So the population of the planet right now is about 6 billion. By 2050, it should be roughly around 9 billion. We expect that, and this is World Bank and type of information that, 6 billion of those 9 billion will live in urban regions. So that's like saying that take the entire world's population of today and move them into cities. Might be some scaling problems, especially if you think about how transportation networks run today. Not that great, right? There's still quite a bit of problems with the transportation networks, with the water networks, with the energy systems, either in terms of, how efficiently they work, how much the cost associated with them, the quality of service that they can provide. Living in this region, you may not feel it. Some of these things here in terms of the lack of even access to energy or the lack of access to quality water. But you have to realize that of these people, these literally billions of people that don't have access, that's what's moving into the cities, and they're moving to try to be able to have the type of lifestyle that we have today, right? So some really interesting and difficult challenges that are upon cities today, and that will be exacerbated in the coming years is what we believe. So we believe this, with respect to what's happening to cities, is something that's disruptive, and there is a need to better understand how science and technology can help cities to manage their systems and so on. Another reason why we think it's important with respect to these types of problems in cities and urbanization is risk. So risk and uncertainty. So everybody's familiar with the financial instability that's been happening over the past few years, and likely also familiar with how things have changed in terms of the disruptiveness of natural events. Right, when a particular disaster hits, it can cause the region to not only for people to die in many cases, but also for things to just cease, right? In other words, because we are dependent on these very large-scale infrastructures, and we are becoming more and more dependent on digital infrastructures. When things aren't working right, then they kind of cease. And that's something that's very different from what used to happen prior to, when you had this kind of scale in urban regions, when you had this much, digital systems that were handling these types of transactions. So we feel like this is another very important reason why it's a problem today, and likely a long-term challenge that we have to address. So that was kind of a little bit about the why. And I'll soon be getting to more, how the technical part of the talk, I promise, but maybe a little bit more setting up. So, there's a lot of people think of different things when we say smarter cities. What is a smarter city? It's a city that's totally wired in terms of the infrastructure and the people. Is it something where it's about, economic stability and growth? Is it about, quality of life and health? And we tend to find that, we go and talk to cities, and they have their challenges, right? The roads are congested. We need to find a solution because it's a huge problem, and it's causing us not to be able to bring new industry into our region. Or they may describe it in terms of, the number of people coming in and out of the city, or, quality of water, or whatever the case may be. So they have kind of these challenges that they face today. but they all have aspirations as well, right? So, and their aspirations tend to kind of boil down to two things. One is that it is about the economics of it. How do they attract industry? How do they attract knowledge workers? How do they keep those there? How do they make the city, how do they meet the revenues that they need to build the infrastructures to service the populations that they have? Or it's about quality of life. They feel like what they have in terms of industry is sufficient, but they will lose people if they're not able to provide a quality of life. If people don't feel like by living in the city they've gained in terms of their health and their ability to support a family and so on. So it tends to be kind of the health and quality of life or money, which is not so surprising, right? Okay, so some good news is that actually there's quite a bit of work that's going on already. Quite a few cities have done really some very interesting and novel things, right? So this in terms of like, solar city, right? An entire district being powered with solar energy. Ireland actually does quite well in terms of its wind energy. So at night, as much as 40% of the energy that's used by Ireland comes from wind. There's quite a few of these. Stockholm did this work with congestion charging, and it sounds draconian, and everyone was afraid, and other cities have protested against it, and yet in the end they did a very nice job of running a pilot and showing people how it could work if they were to do this and have less congestion within the city, and then they turned everything back on the way that it used to be, and the system kind of seized. And then people were happy to say, what, maybe we do have to do something a little bit smarter here. So it's working, but it's challenging because they're one-offs, they're first of a kinds, they're the beginnings, and it's very hard for these cities. They're challenged because, how do you show return on investment for a project that you don't know will really work? That's taking in new technologies, requiring a new way of operating, right? So it's challenging in that sense. And like I said, many of these they're great in terms of a first of a kind, but getting them to really scale, getting them to be replicable to other cities, getting them to interface such that you didn't just fix the power system, but you also fix the transportation and the water and so on, is where the challenge is. The other thing that's kind of interesting, at least from IDC, and I think the reason that I wanted to show this chart is because it's basically saying that a lot of the groundwork for getting the smart metering, getting the instrumentation and sensoring that you would need for the transportation network and so on has been being laid actually for several years, and the expectation is that in 2012 that sufficient of that will be in place to really support some of these more ambitious projects. And the reason that I think that that's important is because, when we first started working on this area, people would say, yeah, it's great, but you know what? You talk about big data, but we can't get the data. I don't have any access to the data. Where is this data that you're talking about? And I think we've hit a turning point in that, the data is being generated. The utilities have the data. They are grappling with the data, and they're realizing that they need help in terms of, analytics and visualizations and ways of kind of coping with the amount of data that they have, and not just coping with it, but leveraging it so that they can do smarter things with their infrastructure. Okay, so now what I want to do is to try to start to transition into a little bit more technical part of the talk, right? So still, a little bit more, I guess I'll say. So so the idea is that we've talked about the problems with the cities and the aspirations that they have. But what does it mean to a researcher or to a scientist or to an engineer? How can we help? And as a research organization, even though we are substantial in terms of size, I started the lab in July of 2010. One person. We're now at about 75 people, so that's quite a number of people that are working on these challenges. But it's very small and daunting if you look at all of the problems that that cities have, and obviously we can't go out and kind of build everything that they would need. So what do we, as a research organization, go after? And what we looked for were those things that would be, kind of, that had a research aspect to them, but also might be the problem that really needed to overcome, that would be difficult to overcome just by, build it type of a mentality, just having people go out and build something. What could we do that was really on the research side of it? And so these three areas are actually defined quite a bit with our strategy and the way we approach projects. So I'll describe those, and then what we do is we tend to take these areas and then we tackle them in the domain of urban transportation or water management or power systems or that sort of thing. So what are the three things? So the first thing is that, as I said, there's a lot of data out there. Transportation systems have been deploying sensor networks for well over roughly 10, 12 years. In terms of some of the more obviously not the third world type, but in cities such as London and Paris and New York and so on, to 12, sometimes 14 years they've been out and deploying these sensors. The problem is someone comes in and they say, okay, so you have a system now, you have GPSs on all the buses. You can tell where all the buses are. That's good. All right, and the next guy comes in and he says, okay, now I've set everything up and you've got these the sensors that are at the junctions of the roads, and they're going to tell you how many cars pass that junction at any given time. So at any given time, any point in the city, you can see roughly how many cars are passing a particular junction. That's great. These two talk to each other. Do you have models that take into consideration both of these data types? No, right? That right now, building these models where you can actually from that have reliable decision making that take in the different types of data is very difficult. It takes humans going out and trying to figure out, okay, what could be a model that I could use to try to represent and bring this information together. So part of what we've been doing is this in terms of data assimilation. So it's basically, by assimilation I mean that it's you have models or you have background information, and you're continuously trying to take in real-time information that helps you to correct your state of the model so that you can give better decision support. Second one is modeling human demand. This is basically trying to be able to forecast how many people will I have to service, how much energy will they consume, or how much water will they consume, when will they consume it, what might be the conflicts. You might think this is very simple and very easy. The problem is that it's always changing. So if you asked me, could I tell you roughly, could I predict the number of cars in the city in London Center, at 8 a.m., for the next week, I'd do quite well at it, as long as there was no event, right? The problem is when there's an event, when there's a disruption, when the water main breaks, right? When when the Olympics come to town, right? When a particular event is happening at the Olympics, then it's very difficult, right? Because you have to take data that's not necessarily intended for that and try to use it to make inferences. So modeling human demand is difficult. The second one, or the last one, is being able to factor in uncertainty. So part of the uncertainty comes from demand. You don't necessarily know the demand, but it actually comes in just about everything. So, we've had, in operations and planning systems, they use optimization techniques. But the challenge is those optimization techniques kind of expect that you know what your variables are. You know what your demand is. You know what the price of energy will be. You know what the rainfall will be, right? So you have the leakage, all of these sorts of things, but they don't, for these systems, they don't know that, right? And they change, right? That's the problem. They're disrupted by events. So what we've been doing also is working on systems that could still operate in the face of uncertainty. So, okay, so now I'm going to switch and give you some very specific examples of projects. Okay, so this is a transportation project that we've been doing with Dublin City, and it's about complex and system analytics challenges. So, as I said earlier, they've been giving us data, truthfully much more data right now than we have models to fully, be able to represent. And so this is an example here. It's an example of just GPS probes in the city. And it's, these are actually dots, right? So each one of the dot is a GPS probe that we got. It's over a period of roughly about, I think this was 1 hour, right? And so right away you start to see things. You see, well, okay, the representation can be sparse in areas. I don't necessarily have all of the roads covered. And the roads in the center of the network are actually pretty well covered, but even as you move out, they're not as well covered, right? So there's a sparsity in the data. And the other challenge is if you kind of zoom in and take a closer look at the dots, well, the black thing is not a superhighway. It's the Liffey. It's the river that runs through Dublin. So the problem is that these GPS probes, they actually tell you over a radius roughly where they are. And from that, what we want to try to do is we want to try to infer how the transportation network is working. What are the speeds? Is there congestion? Is there a change in the speeds and so on? So if you can't, the first thing is, the probes don't tell you necessarily the right information. And what's bad about it is that it would be one thing, and you could easily say, I don't think it takes a PhD to tell you that, the buses probably aren't in the Liffey. Well, at least maybe not that many of them, especially if it's, it's a weekday. There are probably not that many. But the problem is that it's not just that they're showing up in the Liffey. It's that even when we see them on a road, it may actually be on a different road than what we see. And if you think about if you're trying to estimate speed, and this is a bus that's coming on and off and taking different trajectories, because you only get a point that says, I'm here now, and then at some other point it says, I'm here now. So you don't know which path they're taking. You don't know if they're moving over to stop and pick passengers up, so you don't have any of that information. You don't even really know, is this really the right street that they're on? So we've been doing a lot of work to try to first do analysis so that then we could help the decision makers make decisions based off of this data. So, and you might look at this one. So this looks really bad, right? We've got a lot of buses in the building, and that sounds like it's probably a mistake. These buses in the building are wrong, but those buses in the building are correct because that's a bus depot. So it's not necessarily always obvious. There's another example, as I said, we're trying to estimate speed, and it's the same thing. Some of the data is obviously wrong. We know that there are no buses going 350 kilometers per hour through the middle of downtown Dublin, especially if you've ever been in downtown Dublin, that that's not happening. That's at the end of the river. So, but the problem is even at these lower speeds, we don't know whether that data is reliable or not, and so we have to try to cleanse the data. The other problem is that the data is constantly coming at us, right? So there's 1,000 buses roughly, roughly 3,000 GPS probes per minute. We have the video coming in from the closed-circuit TVs, the loop, and roughly 20,000 tuples per second coming in from the induction loop. So how do you take all of this data and be able to continuously process it, not just once? So obviously the idea of an analyst kind of sitting down and saying, okay, could this be happening? It doesn't work with these types of challenges until, except for, when there's something wrong, then you need to kind of go back and analyze it. So this is a project that we've been doing actively actually with Dublin City. This is kind of a demo of how it's working now, how we take that data and try to put it together into, well, what's happening within the transportation network. And this is reflecting the bus network at first. So it's kind of zooming into a particular route. And what it's showing here is on this particular route, there's the different road segments. The green says it's running fine. The red is saying anomalous behavior. It doesn't know. It's running slower than I would expect at this time of day. And what we're doing is, like I said, we're taking in all of these GPS probes continuously. And then what we're doing is we're not only trying to do all that geomatching, so putting it onto a road, the denoising that's required. But we also are predicting. We're trying to predict, continuously every bus, when it's going to, where it is, when it's going to get to the next bus, is it, and when it's going to get to the next station, as well as every other station on its route, and trying to give that continuous picture to the operator. We've done some work in terms of trying to look at, okay, well, can you just show me the ones that are, there's a particular bus speed, for example, so you can select on the bus speed and it filters out those things that are not, according to that bus speed. So we have different filters for being able to do that, different ways of being able to kind of expand out from a route. But there's a lot more work to be done here in terms of coming to a visualization really that people can make decisions from. It's a beginning, but it's a long way away actually. This is showing work that we're trying to do in terms of adding the induction loops in, right? So the problem is it tells you how many cars pass a particular point at a particular time, but you don't know how many are queued up. Is it only a few because there's stuff that's sitting in front of it, and so it can't keep going? Or is it because there's just nothing that's queued up? You don't know. You don't know if the car's going straight. You don't know if it's turning. You don't know if it's a car, it's a bus, or whatever. So a lot of information there. And what we're trying to do is to put that together with the GPS information and with other information so we can give a view of the whole city. Another form of data that we're trying to use is, whenever we highlight a particular segment and we say, look, this segment's gone red, there's a problem here, it's not behaving the way it normally does. What does an operator do? Well, the operator then says, what might be the problem? So they might go out and try to search, well, is there a particular, event, or is there roadworks? Is this the right time of day? They try to use their domain knowledge to figure it out. So this particular project is trying to use information that we can get in natural language sources, right? So blogs, records of events, schedules of events, schedules of roadworks, and so on, and try to use correlations between space and time and other features to say, well, actually, if you're seeing congestion within this area at this particular time, it's propagating back out this way. Maybe in this particular case, it turns out that there was a Madonna concert, so that could affect traffic. But you can see how that particular thing, it's not that the concept is especially hard. It's just that it's difficult to try to get the data in a form where people can make good decisions, and that you can represent it to them so that they're not having to try to visualize and revisualize and revisualize, but instead it gets more presented to them. Because at this scale, they just can't do it. The next slide is what we're actually trying to do is, now that we feel like we're able to get the data in a good representative form, we're now working on how do we use that to actually automate some of the decisions that they would have to make. How can we change the lighting strategy, for example? How can we change the signaling strategy? We have an interesting project that we're doing with pilot cities in Glasgow and in Graz, where we're trying to reroute and change the signals to reroute traffic, not just based off of trying to get people there as fast as possible, but trying to ensure that the routing of the traffic supports kind of a low-carbon society, right? So the idea is that you don't necessarily want to try to always have people coming in routes where there are hospitals and and schools and so on. So can we do a better job of avoiding buildup of emissions in certain areas and include all of these types of factors when we're doing the optimization of transportation in the city. So what I'm trying to do is to kind of give you an idea of the project and to give you an idea of kind of where we are in terms of some of the visualization pieces of it. But like I said, it's what I'm really hoping to do with this talk is to get more people working on these types of problems, because I think it's different, it's exciting, and we have a long ways to go. This is a project where what happens is that if you think of wastewater treatment plants, what they have to do is they're just tasked with treating to a particular chemical index. You treat to this chemical, what you're going to release back into the water body to this index, and you're good to go. Release it into the river or the estuary or whatever you want to do. Sounds like a good idea. They measure once a year if that body is okay, right? And guess what? There are many wastewater treatment plants that flow into certain bodies of water. So what happens when they don't release in a coordinated way, or when there's rainfall, excessive rainfall, and that pushes it, or when there's tidal conditions that pushes the water back into the river or the estuary? So this particular project, the problem is, so what you'd like to do is you'd like to have sensors to understand whether it's a good idea and what chemical index they really should be treating to at any given time. The problem is the water sensors are quite bad because they only measure over a certain area and they get fouled very easily. So this is a particular project that we're doing with this, which is using light sensing off of the surface of the water. And we're trying to build models that would represent the entire bay, the entire water body from that. And then eventually we have to get to the point of, like I said, systems that can support them in making decisions. So the next project is in terms of modeling human demand. So this you're probably more familiar with. It's using telco data, data from smart cards, that you use to navigate the transportation network and so on, to try to understand how people move and interact in the city. This particular study down here was basically looking at if I analyze that telco data, and there are certain different types of events in a city, a sporting event versus a play or that sort of thing. Can I tell where the people are going to come from? And even more importantly, could I predict where they'll go to when the event is over? And the reason is because you could do a better job with scheduling your transportation network if you knew where people were coming from and where they were trying to go to. So actually, it's reasonably good, roughly, like kind of at the 85% level in terms of being able to do that prediction. This is some additional studies in terms of trying to look at what influences how people move and interact and use the city. The top one is the Thames running through London, and it's basically showing that even in today's digital world, a shocking amount in terms of how people interact and find services is still divided according to this geographical feature, the river, right? So it's kind of surprising. This particular one is showing that it's not a good idea in the U.S. You often plan facilities according to city lines or state lines, but people don't necessarily adhere to that when they go and look for services. And so this was just showing that cities sometimes merge, they sometimes split apart, same thing for states. This particular mess here in terms of the middle is basically an origin-destination matrix for a particular region. And the idea is that the way that people get this information right now is they used to get it, is they do surveys and ask people, what's your commute like? Where do you go? Where do you come back from? They do that, every 5 years is roughly the time when they could do that. Well, with this type of data, we could get that continuously. So we're just trying to show how this can help the system. This is a project in the space of energy, and again, it's about modeling human demand. And here, what's happening is that I'm sure you're all aware, renewables, right? So people want to take advantage of of power of wind, of solar, and so on. The problem with these renewables is that they're ready when they're ready. So they basically, when the sun is shining, then you can get power. When the sun's not shining, then it goes away. And that's very different from how people run the energy networks today. The way the energy network is run today, you have a plant and it fires. You have a relatively small number of plants throughout a nation. You fire up the plants and they run and they generate energy, roughly to the forecast that you expect for the day. So utilities are very good at forecasting for the nation. But with renewables, you need to forecast at finer time and space granularity. So we started a project to try to do a better job at forecasting demand at very small granularities. The real thing that I wanted to kind of bring up to you guys was not necessarily that problem, but the bigger problem of, okay, so what they need, what the energy companies are telling us that they need is not forecasting for the nation, but they need what might be tens of thousands to maybe even hundreds of thousands of models so they could get the resolution that they need. How are you going to debug that? How are you going to know that these models really are representative of what you're trying to do, right? How are you going to gauge it over time? How are you going to get information from the domain expert to say, yeah, this is correct, or to realize that there's a problem, right? So the challenge is in terms of being able to create systems where you really could have, tens of thousands or hundreds of thousands of models that could be, created and debugged as part of kind of this development cycle, and then brought into the real time to try to manage the system. So this is, I'll just show you a video. So we've actually done very well at creating a system that can generate models quite accurately. We've done very well at being able to run this so that these models, so that we can run tens of thousands of models on a computer system, and we feel like we can scale it up. But the visualization part, yeah, they're not going to be able to do it from this. Right? This is a line. This is basically exactly what we were forecasting. This is trying to show them the application that they may well need to debug. Yeah, not so easy. So we've got some really significant challenges in terms of, I think we're doing quite well in terms of being able to create some of the models, understand that, build systems, but we're not doing as well on the visualization pieces of this, or the visual analysis, or so on. This is another example in terms of factoring in uncertainty. So decisions with risk and uncertainty are pervasive. So these are just some examples, right? What route should I take? From a citizen's view, if you're trying to navigate the public transport system, or even the public/private transport, what do I take? Which route do I take? Should I drive? Should I take a bus? From the supplier's perspective, how should I choose my suppliers? Should I be worried about, weather at different times of years and so on? Again, from the operator's perspective, when do I shut things down for preventative maintenance? How do I know that something that's unexpected is not going to come up that's going to make that turn into a very bad decision? We're also looking at it in the context of social care, right? How can we look at the risk factors that are associated with different social programs and factor this in to try to help people build systems that would help the citizens of the city better. We're doing quite a bit or we have a project also where we're looking at this in terms of healthcare, right? So if you think of, what do you mean risk and uncertainty in healthcare? Okay, well, think about it. You run a test. If you've ever kind of really had to go to the doctor and where it's not something that usually you get a test back and they say, okay, well, I got this result from this test, so I've scheduled these other 3 tests for you. And then you get the results back from that and you say, okay, well, then I've scheduled these additional tests. So there's actually quite a bit of uncertainty. Unless it's something that is, that just jumps out the first time, it's very difficult. There's uncertainty and risk, both in terms of the results of the tests, the diagnosis that they arrive at because of that test, as well as the treatment plans, right? So there are usually more than one ways to treat a particular disease, or at least different plans for doing that. And different ones have different risks. And how do you represent that, understand that, communicate that to the doctor and to the patients? So this is a particular project. I'm sorry, I'm kind of running through these very quickly. I don't know if is this okay? Does anybody have any questions or anything, or I'll just keep going quickly? Okay, it's pretty warm in here. Yeah, and it's pretty late in the day for it to be this warm, right? So anyway, I'll try to keep going. Okay, so one of the spaces where we're looking into this is in the water space. And you would think that the importance of water has to our health, that, these systems, in terms of the water that gets brought to our household, how it gets treated and then brought back into the river basins and then, treated again and brought back into the home, should all be, well connected and organized and managed. No. They're not. Different utilities, different services, different strategies, different plans, generally often not even communicating them, to be quite honest, which is kind of a scary thought. And what's even worse is that they just have different stressors that they have to try to deal with that aren't necessarily conducive to working together as a single ecosystem for the network. And to make things worse, they have a lot of uncertainty. So to give you an example, one of the things that's causing a lot of change in the way that people manage water in Europe is EU water framework. And basically it's starting off with things like, well, you at least need to know your water bodies and the quality of your water bodies and that sort of thing, if they're going to be used for supplying the population. So even that is not there in many cases. You need to be able to measure if there are conditions that cause overflows such that sewage goes into these water bodies. You should know that, right? But in many cases they don't, right? They don't have the measurements set up for that. So the EU water framework is going back and saying, look, you're going to have to do these things. You have to measure these sorts of things. And guess what? If you're not measuring them, or if you're not meeting the certain standards, I'm going to fine you, right? So, which it's not, sounds rough, but the point is that if they're not doing them, maybe they do need a little bit of incentive to try to take on these things. So if you look at, in many cases, the systems just aren't there in terms of being able to know that when there is overflow, that it's not going to leak. It's just not there. And so and the problem is, like I said, it's, the demand, the rainfall is changing every year. It's changing every season. And so how do they plan for what they should be doing? How do they allocate their resources? Because these are physical infrastructures that are very expensive to lay new pipes, to install new pumps, to maintain them over the life of them. So what's the strategy? It's very simple. Do whatever is the biggest fine first. And the problem with that is that the fines that you had to pay, what caused you to pay fines this year is not necessarily the same events that are going to happen next year. And so, they're chasing a moving target. And so, what we've been trying to do is to try to build systems that would take into consideration all of this uncertainty and give them plans instead of saying, if you take the optimization techniques, usually what you do is you provide specific numbers for each different variable. You run optimization, it says the answer is 7. That's your answer. But if you have, ranges and orders of magnitudes and these sorts of things, what you really need is you need a system that can take those types of information, those types of models, run the optimization, but probably even more importantly, instead of saying the answer is 7, you need something that will say, well, as long as your values fall within these ranges, then this is your optimal plan, and your cost per unit is going to be this. But if this goes outside of the range, and it has, within 10 years, then your unit cost is going to soar to this. And so you need to think about a plan that hedges against risk. And so this is the next area that I would like to try to motivate people in working in, is that representing risk and uncertainty for someone who's trying to make decisions is very complex. It's very difficult. To give you an example of just how difficult it is, if someone tells you there's a 10% chance of rain, do you know what to do with that piece of information? Right? You don't know exactly what to do with it, right? And that's pretty basic, right? And we've been getting that for generations, for decades. That's the information we've been getting, and yet we don't even know how to deal with that. So, carry an umbrella. Yeah, it might be a little higher than 10% though. So anyway, so we've been working on a project that tries to do the optimization pieces of this, and we've done pretty well in terms of being able to address how do you build algorithms that are scalable, that can compute these values efficiently. We've done fairly well at bringing in the uncertainties, but in terms of a system that really takes information, this is the system that helps someone to build a scenario, to model the information that they need to bring into the system so that it can run its optimization. There's something to be desired here, right? So I'm not criticizing the work here. It's just that it's for someone who understands kind of the numbers and the algorithms and so on behind this. It's not for someone who works in the water department, right? And that's what they need, right? So we've been trying to work on this. This next visualization is actually it's on a very different idea. It's basically what it's showing water consumption in Dublin, and it's up at the top is showing you how it's going in terms of time, right? So the day of the week and over time. So obviously, what you're going to see is that as the day starts up around 8 a.m., then it starts to go up, and then obviously at night it's going to start to collapse back down, and you'll see differentials in terms of how much is consumed on weekends versus during weekdays and so on. So this was actually created for an exhibition at the Science Gallery. So it was they asked us to try to help in terms of they were doing an exhibition with awareness of the water shortage, right? And so this was to try to give people a sense of when you turn on the tap or when you leave something running, it's always the city is always kind of sucking water in, right? And then there's the challenge of then cleansing and purifying and getting that back out to to the body so that it can be brought in again. And the reason why they were trying to do this is because in Dublin, you don't pay for water. The idea is that water should be a right. It's all around them, right? I mean, Ireland, should they have a shortage of water? What's interesting is that they actually are having challenges with water. They're having to go and tap in, in water sources that they haven't done before. And, people are up in arms about it because these are, Ireland cares a lot about maintaining, pristine environments. They're a tourist, country. They get a lot of tourism. And so they have big concerns about this. But what they were trying, part of the reason for having this exhibition was to help people to understand, well, water is all around us, but the cost of cleaning and distributing and then, pulling back that water, that's not free. That's not all around you. It takes power, it takes infrastructure, it takes maintenance. And so you need to, if you're not using the water, you need to turn off the tap because that's often the problem is that people just, with not metering water and not charging water, is that if the tap is broken, why should I spend the $24.95 to fix it? Because the water doesn't cost me anything. Just let it leak, right? So that's a bit of a problem. They are changing that. So it's nice in terms of artistic, but obviously no one will be able to do any kind of problem determination from that, or make any decisions, based off of that. So we see capabilities in certain areas, but not in others. So this is just talking a little bit more about what we do for risk, and our idea here is to try to say, can we make an understanding of risk and uncertainty, can we make it pervasive in our tools and make it such that people can operate under this, and how do we go about doing that? So we're doing different projects, right? Trying to make it simpler to create risk models. So basically, if you think of risk models, where would you get information about the price of energy? Well, you could get it by studying, building a statistical model. Where would you get information about, risk associated with different diagnoses and treatments? Well, there are documents that describe this, research documents that describe this. So this is basically about trying to use, statistical modeling, natural language processing, and these types of techniques to bring in the risk models and automate that so that these algorithms can be run. We're trying to make it easier for when the domain expert has to try to express that I see the model, I understand that's what it's telling me, but it's wrong because it's not taking into consideration these factors. So we're trying to think about ways that we can elicit risk information from people in a way that's more intuitive and more from a domain expert's perspective. Of course, we're working on scalable algorithms to do this, and we're working on how can we communicate risk, how can we express that in a way that whoever needs to deal with the information can do so. Another project that we have, when Dublin came to us and said, we'll give you access to all our data, we said, that's fantastic, but if we could get this out to other people, that would be even better, because then when we release an algorithm and say it performs at this with this data, then other people could compare their algorithms to that. So we did this work in terms of Deblinked, which is a website where we're basically releasing as much data as they'll allow us to release. It turns out now that a lot of cities are doing this, so the amount of data that's out there and available for cities, especially if you go look, London's website, Washington, D.C., San Francisco, there are a lot of cities who are really putting a lot of data out there. The problem is they put out spreadsheets. They just put out data sets. How do you really use this? How can you find the ones that might mean something is challenging. How can you find correlations? How can you try to do that? So we've been working on projects that would basically try to put a layer, use analytics to put a layer on top of this such that people can find what they're looking for. So semantic analysis types of techniques to try to label the data, for example, is one area. One of the areas that we've been doing as well, this is a bit of a visualization. It's basically showing, can we use some of the data that we can get from blogs and from event information that are provided to the city to understand sentiment within the city? And can we help the people who run the city understand the sentiment in the city? Who's talking about what? when they talk about, a new build or services, what are they talking about? When do they talk about it? Where does it, where does it seem to be the sentiment especially good or bad or that sort of thing? So here again, I mean, it's not necessarily, it's the beginnings of trying to represent all of this information. But as you can see, it would be very difficult for them to try to make decisions based off of this level of information. So I think it's, like I said, I mean, I think it's, we have a lot, there's a lot of open space in this. And so we are hiring researchers through really senior PI level researchers all the way through recent PhD graduates. And I didn't know how to express it I put research software engineers, but it's different. It's not the form of a software engineer where it's like the waterfall model where you have kind of a specific product that you're trying to develop to. It's people who love to build things, to prototype, to pilot, to take into consideration a lot of the the math techniques as well as building a system. So it's a different type of programming. They need to understand tools so they can understand what they can scaffold versus what they need to actually build from. So with that, I hope even if you're not interested in joining us, I hope you're interested in trying to maybe think about some of the challenges in this space, because I think it's an excellent space, and I think it will drive visual analytics maybe in a different way. This the fast data and the continuous analysis and that sort of thing. So and especially the visual analysis, not just for investigation. And I'm not saying that's all you do, but visual analysis for design and decision making and solution, building solutions and that sort of thing. So that's all I have.